Okay, this is Giancoli Physics, AP Edition, 7th edition. We are in Chapter 10, Fluids, working on problem number 47. Let's go ahead and jump into it. That problem reads, what gauge pressure in the water pipes is necessary if a fire hose is to spray water to a height of 16 meters? So go ahead and wrap your brain around that problem. Come on back when you're ready to compare your plan. Okay, let's see what you came up with. Now for this problem, it wouldn't be out of the question to start with the hydrostatic variation equation, which is essentially this one. However, since this is the Bernoulli's equation section of this particular textbook, I'm going to go ahead and start with Bernoulli's equation and show how in a previous problem we showed that this Bernoulli's equation collapses down to this smaller, simpler version when there is no flow. Because there is flow in this pipe, obviously, but they're comparing the gauge pressure, which again is a differential pressure, to spray water to a height of 16 meters. Well, at the 16 meters, there is no flow because if there was flow, you'd still be rising higher than 16 meters. So that is the highest it's going to get, but you'll have zero velocity at that point. And then as far as the gauge pressure goes, the difference between these two pressures, again, the gauge pressure, this is the pressure head at the front of the pipe. So you can essentially consider this to be zero flow. Think of it as a large water tank that has very low velocity compared to the pipe. So again, there's flow in the middle. There's going to be velocity flow between your pressure head and the height that you reach, but there's no flow at the 2 points that we're comparing. This is similar to an energy balance where you don't really care what's happening in the middle. You just want to compare the two ends. So we're going to consider the velocity to be zero. Now, technically, is there a pressure difference due to the atmosphere at the 2 points? Yes, because there is a height difference. But given that water is 800 times more dense than air, that's several orders of magnitude. So we're going to ignore any additional pressure due to the air. That will be our differential pressure on the left. When you take y2 minus y1 here, that's going to be your change in height for rho gh. And again, we're down to the simpler version of this equation after applying Bernoulli's equation to our scenario. Gauge pressure is what they're asking for here. We just need the density, acceleration due to gravity, and the height, which we have. If you don't recall the density of water, you can look it up in table 10.1 for this textbook, or use your favorite search engine. But water is 1,000 kilograms per cubic meter. We are still on Earth as far as we know. There's our acceleration due to gravity on Earth. And if we're going to a height of 16 meters, we're going that high. Now this is roughly 10. We'll call that roughly 15. That's 150. That's about 15 friction. 150 times 1,000. That's 150,000 roughly pascals we should get. Let's go and pick up our calculators and see what it tells us. And as expected, after punching those numbers into our calculator, we get 1.568 times 10 to the 5th. That's all in SI units, so that's going to be pascals. If you take this kilogram here and that meter there to cancel out one of those meters there, you get a kilogram meter per second squared, which is a Newton, divided by a square meter, which is an area, a Newton per square meter, which is a Pascal. That's where that comes from. So with our significant figures, we'll round that to 2 units. Our differential pressure, or gauge pressure, will be approximately 1.6 times 10 to the 5th pascals. Now, they didn't specify units here. Gauge pressure is typically represented in PSI. I believe the back of the book actually has this in pascals. But if this were more of a real-world situation, you'd want to go ahead and convert this. You can look this up with a search engine or look in the table in the book. You have one correction. 14.7 psi for every atmosphere. And 1 atmosphere is also equal to 1.013 times 10 to the 5th pascals. And if you crunch that out, that's about 1.5. So you'd get about 20-ish, 20 to 22-ish on your pounds per square inch. Let's go ahead and crunch that out just in case. Now, to be clear, I didn't use this rounded number. I used this extended number with all the digits when I performed this calculation. And when you do that calculation, you get about 22.75 psi. Again, we'd round that to 2 significant figures and call it 23 psi. And that should do it for this problem. We're on to the next.